In section 4.3.2, we're going to continue the process of solving these higher degree polynomial equations using our calculator and synthetic division, but we're going to add one more layer to our understanding, and that is factoring completely. As a reminder, recall that if x equals k is a zero of a polynomial function p of x, then x minus k is a factor of p of x. Therefore, once all the zeros of a polynomial function are known, the polynomial function can be factored. Example 2. Use your graphing calculator and synthetic division to find all zeros of the following polynomial functions. That part's going to be the same as the previous examples we've completed. Here's the new part. Then factor the polynomial completely. So notice on example A, f of x is a third degree polynomial. So we are expecting at most 3 zeros. This is degree 3. We can therefore expect at most 3 zeros. Remember, when multiplicity is considered, we may have less than 3 distinct zeros. Let's go ahead and type this function into our graphing calculator to get a place to start. We want to look at the x-intercepts and use those to reduce the degree of the polynomial with synthetic division. Okay, so with our function entered, we can graph the polynomial. And remember, when we're finding zeros, we're looking for x-intercepts. So here's the graph of our polynomial. Notice that it crosses the x-axis 3 times. So we can expect each zero to have a multiplicity of 1. I'm going to start on the positive side of things. Notice on the far right side, 1, 2, 3, 4, 5. It looks like 5 is a zero of this polynomial. Now, we still have to confirm that with synthetic division. In case the x-intercept is just to the right of 5 and we can't see that accurately with our calculator, we can prove that it's a zero analytically using synthetic division. Also, in the process of synthetic division, we're going to reduce the degree of our polynomial, making the problem easier and easier as we go. So here we are, set up for synthetic division. Remember the process. We take the number in the box times the number on the baseline, find that product, and then add vertically. So on the next step, 5 times 4 is 20. Negative 17 plus 20 is 3. 5 times 3 is 15, and negative 15 plus 15 is 0. So this means that 5 is, in fact, a zero of the polynomial. So I'm going to make a list over here. X equals 5 is a zero of the polynomial. Now, remember, if x equals k is a zero of the polynomial, then x minus k is a factor. So at this point, we can keep up with our factorization. Developing this factorization, we know that of our original polynomial, I'm just going to rewrite it over here, one of the factors is going to be x minus 5. Now, if x minus 5 is a factor, where's the other factor? Well, the other factor is in disguise on this line right here. Remember, this line represented a degree 3 polynomial, so the result after one round of synthetic division is a degree 2 polynomial. So I can take those coefficients and assign descending powers of x to determine the other factor. At this point, you've got 2 choices. You can either factor this directly, or you can continue the synthetic division process and factor in this non-traditional way. I'm going to continue with synthetic division because it's fast and efficient, and you may find that you like the synthetic division method of factoring better than just the traditional method of factoring. For those of you out there that aren't a big fan of factoring, here is a new solution to an old problem. Looking at this function, notice it also crosses the x-axis at negative 1. So I am going to confirm with synthetic division that negative 1 is a zero. Remember, on this round, we're going to stop just short of our previous remainder. Bringing down the first 1 and multiplying negative 1 times 1, we get negative 1. add vertically to get 3. Negative 1 times 3 is negative 3, add vertically to get 0. So we have confirmed, because the remainder is 0, that another one of our zeros is x equals negative 1. Now, if x equals negative 1 is a factor, that is a 0, the corresponding factor is x plus 1. So I'm going to come over here and I'm going to continue my factoring process. Remember, this second degree polynomial, which we had here, we now know another factor is x plus 1. Remember, whatever the 0 is, you change the sign in the factored form. Well, what's the other factor that corresponds to this polynomial? We know this, after another round of synthetic division, is degree 1. So I can use these numbers and assign descending powers of x, starting with x to the power of 1. We get 1x plus 3. Now, notice on our graph, the other 0 or the other x-intercept on the graph was negative 3. So notice, if you want to confirm this, you can do it very quickly with synthetic division. So we know x equals negative 3 is a 0, therefore x plus 3 is a factor. So our third degree polynomial function has now been factored into 3 distinct linear factors. By linear factors, I mean each x has an exponent of 1 in the factor. So to be official, let's go ahead and list our zeros. We have the polynomial function factored. The zeros are 5, negative 1, and negative 3. I didn't get those in order left to right, but that is okay. So as you're working these problems, you have a choice. You can continue with the synthetic division process all the way down to this last spot, and then take each one of those zeros that we have listed over here, list them in a solution set, and from those zeros form your factors by subtracting each zero from x. Or hopefully you were able to follow the development of the factoring process like we did over here as well. Okay, let's practice that again. Example B, r of x equals 3x cubed plus 5x squared plus x minus 1. How many, here's a pop quiz, how many zeros should I expect? And how do you know? Well, it is a degree 3 polynomial, therefore we should expect at most 3 zeros. Is that what you said? Also, this means we can expect at most 3 distinct factors. So I'm looking for 3 factors. To get started, we're going to graph the function with our graphing calculator. So I'll type this in, 3x cubed plus 5x squared plus x minus 1, and we'll take a look at our graph. Now, hopefully you're thinking, you know, these are big polynomials, but this process really isn't too bad. In fact, it's kind of fun, right? It's like putting a puzzle together. We're just finding all the pieces of the puzzle. So this one is a little bit different. It is a degree 3 polynomial, but it looks like the graph bounces at one of the x-intercepts and crosses at the other. To be sure, let's zoom in just a little bit. So I'm going to type zoom, option number 2, and then press enter when I get back to the home screen. Sure enough, it bounces at negative 1 and then crosses at some fraction value. Now, by looking at the graph, it looks like it's about 1/3, kind of close to 1/2. I'm a little bit unsure about that one. So I'm going to go with what I'm sure of, and that is the graph crosses, or I'm sorry, the graph bounces at negative 1. So I'm going to use negative 1 to start my synthetic division process. In this portion of the process, we are verifying that negative 1 is or maybe is not a 0. So from synthetic division, because our remainder is 0, we have confirmed that x equals negative 1 is in fact a 0 of the polynomial. That means the corresponding factor is x plus 1. But remember, from the graph, we observed the graph bounces at negative 1, which means the multiplicity of that 0 is even. So I should be able to divide it out again and prove that it is a double root or a repeated 0. Let's see what happens here. Yep, we have confirmed it again. So I have a repeated 0 or a 0 of multiplicity 2. Now, in fact, I'm going to use this remaining factor to find the remaining 0. So let's go back through our process. This was a degree 3 polynomial. After one round of synthetic division, the result represents a degree 2 polynomial. So this guy is linear or degree 1. So let's use what we have here to convert into factors. F of x is equal to the factor that corresponds to x minus 1 is x plus 1, and the factor that corresponds to x minus 1 is x plus 1. There's 2 factors. Remember, we need 3 factors. The other factor is right here in disguise. Those 2 numbers are the coefficients of a degree 1 polynomial. That means 3 times x minus 1. So this polynomial has now been factored into 3 factors. Remember, degree 3 means 3 zeros, 3 factors, and that's what we end up with here. Now, do you know what the other 0 is? We can see that negative 1 has multiplicity 2. But what's the other 0? Well, the other 0 we can obtain from this last factor. If I set that factor equal to 0 and solve for x, we can see that 1/3 is the other 0, and that one has multiplicity 1. If I wanted to go back and verify that with synthetic division, I certainly could over here. We could use 1/3, bring down this 3, multiply, and we have confirmed that it is in fact a 0. So we have 3 factors, and by the way, let's go back and refine our factorization a little bit. What we had there was fine, but we can simplify it a little bit. Maybe you already did this, but let's call it x plus 1 quantity squared, since there's 2 of those, times 3x minus 1. That's a more concise factorization. And then we can see the multiplicity 2 there reflected in that exponent. All right, hope you're getting the hang of it. Just as soon as you get comfortable, then I'm going to throw some fractions at you. Let's look at this last example. If you want to pause the video and try and work this problem yourself, you're welcome to do that and turn it back on and check your answer. Or you can leave the video playing and working it right along with me. So what I'm going to do, as we always do, we're going to start with the graph of our function. I hope that this makes you appreciate your graphing calculator. What would you do if you did not have a graphing calculator? How would you solve this polynomial equation if you didn't have a place to start? Well, there's a theorem called the rational zeros theorem that you could use, or you could just take a guess in the dark. Maybe 3 is a solution, maybe 2, maybe -1. You could use those, test them out with synthetic division until you found a winner. Now I'm looking at my graph. Previously I changed the viewing window. I'm going to go back to Zoom 6, the standard viewing window. And observe this graph crosses the x-axis 3 times. So we know that each 0 is going to have multiplicity 1. So we're going to have 3 distinct zeros. I'm going to start with the leftmost 0 this time. Looks like it's crossing at -3. So let's verify that -3 is a 0 of this polynomial using synthetic division. Now keep your calculator handy. You might need it on this one. The process is going to be the same. Multiply the number in the box times the number on the baseline. But remember, you always have your calculator to help with the arithmetic. If you don't need it, that is awesome. If your brain is tired, then remember you can just type this into your calculator, use your math fraction option. It makes it really easy. Okay? -3 times -3 halves gives us +9 halves. -11 halves plus 9 halves is -2/2 or -1. And -3 times -1 is +3. So we have confirmed that x equals -3 is one of our zeros. Now over here, if we want to keep up with our factoring process again, or you can wait and find all the zeros and do this at the end, whatever makes the most sense. But we can say x plus 3 is one of the factors. What are the other factors? Well, we got to find the zeros. So at this point, this degree 2 polynomial can be expressed like so. At least you can see the development of our factorization. Now, looking back at our graph, picking out another 0, the one between -1 and 0 looks like -1/2, but I'm unsure. I'm going to put that off till the end, and I'm going to choose the one that clearly crosses at an integer. It looks like +2. So let's confirm that with synthetic division. 2 times 1 is 2. -3/2 plus 2. Think -3/2 plus 4 over 2. That would give me +1/2. And remember, feel free to type that into your calculator to verify your arithmetic. 2 times -1/2 is 1, and we do get a remainder of 0. So we have confirmed that x equals 2 is another factor. So looking at our process over here, x plus 3 was the first factor. Now, breaking down our quadratic, which was represented right here, we have discovered that x equals 2 is a 0, therefore x minus 2 is a factor. Well, what's the factor that goes with that? This guy is now degree 1. We can write that as x minus 1/2. And from our graphing calculator, x plus 1/2. It appears that -1/2 is an x-intercept. Just for good measure, I'm going to verify that with synthetic division to be super confident, and we are good to go. So we have 3 distinct factors, and we can also list our zeros as -3, +2, and -1/2. So remember that your zeros have the opposite sign as what you find in the factor, and that is simply because when we set that factor equal to 0 and solve for x, we end up moving that number to the other side. So there you go. You just found not only the 3 distinct zeros of this third-degree polynomial equation, which means you've also found the x-intercepts of that function, but you also factored a degree 3 polynomial function, and it really wasn't too bad with the synthetic division process. So keep practicing. The more you practice, the more comfortable you'll become with this method.